So this is equal to, I want to have the numbers over there. So let's make it 4 divided by 10. Right? So 0.4 is 4 by 10. And okay, there is a minus log to the base 2.5. Okay, so we can see that, right? I am trying to find the sum of n number of an infinite series where the first number is 1 by 3 and there is a ratio, common ratio between each term is also 1 by 3. So if you remember, what is the simplification? This is a divided by 1 minus r. So a is equal to 1 by 3 divided by 1 minus 1 by 3 because r is also 1 by 3. Okay, so this is the simplified version of that infinite series over there. Right now, let us try to further simplify. So we have a minus over there. So if you have a to the minus x, right, the a to the minus of whatever log, right, this can be written as 1 by a to the power x, right? So let us try to apply that here. Okay, so this is 10 by 4 to the power log to the base 2.5. So 1 by 3, let us try to make a simplification here. 1 by 3 divided by, this is 3 minus 3 minus 1, right? So that is 3 minus 1 divided by 3, denominator. So this can be written as equal to 1 by 3 over 3 minus 1 is 2, right? 2 by 3. 1 by 3 over 2 by 3. So this cancels. So this is half, right? So I can write log of 2.5, sorry, log to the base 2.5 of half. So what is 10 by 4? 10 by 4 is actually 2.5, right? So 2.5 to the power log to the base 2.5 of. So apply a to the power log b to the base a is nothing but b itself. So here I can see b is half. So the answer is equal to half. All right. Right. Let's move on to the next topic. All right. The next topic, which we have to discuss now, is called as the characteristic. Characteristic and Mantissa. Right. So the very important part of an algorithm, a logarithm, is called as a characteristic and a fractional part, right? That is called as the decimal part is called as a Mantissa, right? So let me try to write that over here. The integral part of a logarithm is called as the characteristic. Right? And there is always, you are going to see a fractional. So the fractional part, or you can actually call it as even the decimal part. Okay, of any log is called as the 97. All right, now let me try to log n. N is a number whose log I am taking. Any base is fine. So we always try to write this is equal to some integer, right? So this integer can be positive or negative. Doesn't matter, it's fine, right? An integer part plus a fraction. Now you look at the condition, this fraction has to be always positive. I cannot make a negative term here. So if somehow there is a negative term for fraction, right, comes up, means I have to, right, make it positive, right, by using some kind of representation. All right, so let us try to look at this. All right, now let us try to go for an example. So this is the example. So let us try to take the log of, right, this is 0.00895. Let us say this is the, I want to take a log of this. So I have not mentioned any base, means it is base 10. Okay. So this comes to be minus of 2.0481769. Let's say. All right, this is what is my answer. So you see, this whole complete number is negative. This is minus 2 minus this. So how do you write this? I want to separate the what you call as the integer part and the fraction part. Let us see. So I can try to write this as, so this is equal to minus 2. See, it is not like minus 2 plus 0.4. It is minus 2 minus 0.4. 81769. Now you see that what is the fundamental rule for writing the what you call as the characteristic and Mantissa of any log. I'm fine with this. I'm fine with this because, so we are fine with the minus 2. That is because it can be, it's an integer, positive or negative. Right. But if I look carefully, right, the Mantissa part, which is expected to be a positive quantity, right, that is not positive, right? So I can see that my rule says it always has to be positive, but right now I have a minus term. So because of which now I am not able to write it in the characteristic Mantissa form of a given log. All right, so let us try to make it positive now. How do you make it positive? Just for this number's sake, right? I can make it positive if I add, say, plus 1 to that. Okay, but when I add plus 1, it actually changes the number. In order to bring it back, you subtract 1 from that. So this is the logic. Whenever I have to, I face this situation, simply add plus 1 and minus 1. Okay, the minus 1 you can definitely add with the integer because this still is an integer. Minus 2 minus 1 becomes equal to minus 3, right? Then this 1 can be added with minus 0.4 to get a positive, right, answer. So that is plus, when you do this, you get plus 0.9518 231. So you can see that I can try to write this log in this format. So this implies the characteristic is minus 3 and Mantissa is equal to 0.9518231. So this is the required answer. This is how we convert. But So there is another standard notation. We find this in many of the books. So which says that log of 0.00895 is equal to, you see this notation, the -3 will be written on the top. So this is like 3 bar dot 9518231. So right, so there will be some representation like this also, right? Don't get confused, it's one and same. So instead of writing it as -3 plus 0.95 95 whatever, they write as 3 bar, indicating that that part is a negative because it is a characteristic of the given log answer, and the positive part, that is 0.9518, will written as. Okay, let's move further. We have something to note. This is a straightforward concept, easy concept, but there are some modifications. So we'll look at that in the form of a note. Okay, now, so the first point under the note, let us say if a number is considered that n is greater than 1. All right, then the characteristic of that log n will be 1 less than the number of digits of the integer part. For example, I'll come back to that now. So, but first let me write the point. So if n is greater than 1, then the characteristic of log n, all right, this will be one less than the number of digits in the integral part of n. All right, let's try to write. Right? So that means, let us take an example. So I'll try to take the log of say 235.68. So this comes to be 2.3723 227. So you can see that this is very clearly visible. It is 2 point something. They are saying the same thing, right? If the characteristic of log n will be 1 less than the number of digits in the integral part. So in case of 235.68, right, how many digits are there in the integral part? So the number of digits in the integral part. What do you mean by integral part? It is the digits of the whole number, right? So 235 is the whole number, right? So that means it is in the integral part, I can write this is equal to 3. And it says that according to this rule, number of, it is 1 less than, right? If it is 3, so the characteristic is 1 less than that. So therefore, I'll just highlight the 1 less than part. So therefore, the characteristic is equal to 3 minus 1, that is equal to 2, which is actually directly can be seen. So no problem with the method. So this is what we need to understand. For any number which is greater than 1, this holds good directly, right? I don't have to worry about how to find out that. Just look at the number, right? If I give a 4566 point something, point say 38 or whatever is, what is the characteristic of this has 4, so the answer is 3. Directly you can write, you don't have to, right? Keep searching for the answer of the, what do you call it, how to find the log. right? You don't have to worry. Directly you can write. That's the first part. Okay, then let's move further. Same thing can be applied even for a number which is right lesser than 1, but it is more than 0. If at all we have an example like that, then also we can find the characteristic very easily in a straightforward technique, right? Let's look at that. So this is if say 0 less than capital N less than 1. If this is the condition, right, the characteristic of log n is definitely going to be negative. That is the first point. And the numerically 1 greater than the number of zeros. Number of zeros immediately after the decimal point, right? Let us go to the example. I want to consider log of 0.0000279. So the answer I'll write. So when I convert this in the normal procedure, right, you take its log, you get an answer, right? If you have a negative part for the, right, after the decimal point, you convert into positive. After that, you try to write this in the required format. What is that required format? Required format is the characteristic and Mantissa. When I write in that way, I'm going to get this answer. I'm writing the answer directly. So that is 5 bar indicating negative 5 point. This is 4456042. So now actually you are what we are trying to look, what you are trying to find out is this answer. So how you are deciding at it is minus 5, right? It can be directly understood that it is minus 5 because, right, you have to trace out how many number of zeros you have immediately after the decimal point. In the sense, continuous zeros if you have, only that will be considered. If at all you have a 209 like that, that will not be considered, right? Until you get your first number, how many zeros you have. So you can see that there are 4 zeros, right? There are 4 zeros. I have to add plus 1 to that. That is the 5 and it is negative, right? So you can see that log n is negative and numerically 1 greater than the number of zeros immediately after the decimal point, right? So I definitely have 4 zeros plus 1 and that plus 1, right, will be used here. So that plus 1 will be used here as an additional term which you are going to use, right, and calculate the 5 and it is going to be negative by the rule. All right, so that's how we decide this. Then let us go to the next note. Okay, if the characteristic of any term log n, say let us say it is n, then the number of digits in n is always, right, n plus 1. Okay, then let me write it in a different way. Okay. Is, okay, the number of digits in n, right? This will be equal to n plus 1, one more than that, if, right, the n is greater than 1. Okay, and this is the first part. Then let's go to another note which is very similar to this. So if characteristic of, say, log n is, say, minus n, it is negative, right? This implies there exists n minus 1 number of zeros after the decimal point, right, in n. So this is the negative part of this. So 0 less than capital N less than 1 is a must-have condition. Okay, so where is the application, right? How do you apply these things in a real time or real problem? So we go for a problem where we apply all this. So if say log 2 is equal to 0.301 and log 3 is equal to 0.477, right? Then find the number of digits in 6 to the power 20. Okay, so how many digits are there in the answer of 6 raised to the power 20 is the question. Okay, all right, let's try to find this answer. So P is equal to, so let's try to write P is equal to 6 to the power 20. So 6, I try to split because 2 and 3 are given. So this is 2 into 3 raised to the power 20. All right. So what I want to do now, I'll take log. Log P is equal to, this is log 2 into 3 to the power 20, which we can write as, if there is a power, definitely we can bring it down as 20 log of 2 into 3. So there is a fundamental rule in log that if you take a log of product, right, that becomes sum of the log. So 20, I'll take it out, into log 2 into log of 2 into 3 is simply log 2 plus log 3. So log 2 and log 3 have been given. So you see this is equal to 20 into substitute. So this is 0.301 plus 0.477. Right. So this means this is equal to 20 into, so this comes to be 0.778. Okay. So this comes to be 15.560, right? So that is the log of the required answer. when I say the log of the required answer is this, I just have to look at the characteristic. Characteristic is 15 and it is definitely 2 to the power, 6 to the power 20 is a positive number. So I'll go back to this. So if the characteristic of this is n, then there will be the number of digits in n will be n plus 1. Right? That's a very clear point, right? We understood from the concept of characteristic of a positive number. So this is a positive number. Characteristic is 15, implies the number of digits in p equal to 6 to the power 20. 6 to the power 20 is equal to 15 plus 1, that is equal to 16. All right, let's solve another question of a similar type. If log 2 is equal to 0.301, all right, find the number of digits in 4 to the power 17. Okay, here the answer equals to 11. All right, let's move on to the next question. Find the number of zeros between the decimal point and the first significant digit of 0.036 raised to the power 16. So this is the question. So here, basically the log 2 and log 3 are considered as a very standard terms. So we need to remember, even if it is not mentioned, we should be able to recall and write those values. That's what is expected here. Okay, always the problems will be given if they are not mentioning the values of the logs. So it will be in terms of 2 and 3 only. They will not give any complicated questions. All right, so just remember. So we'll start with this. So let's say P is equal to, this is, okay, P is equal to that number which they have given. So that is 0.036 to the power 16. So I'll take log on both sides. So log P is equal to, this is log of 0.036 to the power 16. So 16 comes down, 16 times log of 0.036. All right, so anyway, I don't know the value of a log of 0.036. I have to write it in some fashion. Okay, so this is equal to 16, we'll take it out into log of, so let's do calculate the 36 first. So divide 36, so this looks like 2 into 18, 2 into 9, 3 into 3, 3 into 1. So this is 2 square into 3 square. So that is 36, right? First, let me write this as 36 divided by 1000. Okay, because 0.036 is 36 by 1000. So 36 by 1000 is my number. Okay. The next step is that now I'll try to write 36 in the required format. So this is 16 log. So 36 is 2 square into 3 square. 1000 is 10 cube. Right. So let us try to write it in the required format. So this is equal to 16 into, so I have a product and division that is happening inside the bracket, right? So I can try to write this as log 16 into log of 2 square plus log of 3 square. And if you are dividing something that is negative, okay, minus log of 10 cube. Right? So this is how we try to represent them. So that means I can still write this in the following notation, and let's try to simplify further. So I know that log of 2 square can be written as, so this is equal to 16 times. So log 2 square is 2 log 2 plus log 3 square is 2 log 3 minus 2 log 3 minus, this will be 3 times log 10. Everything is to the base 10. So let's substitute. So 16 times 2 into log 2. We know that it's a standard value. I should be able to substitute. So that is 0.301 plus, once again, 2 times log 3. So log 3 is a 0.477 minus 3 into log 10 is 1. Okay, so log 10 to the base 10, it's like log a to the base a is 1, right? So that's why it is 1. So simply let us try to write this. This is the first half is 16 into, all right, so this can be simplified as, I'll write the positive part first. So simplification of the positive part gives you 1.556, and there is a minus 3. So let me not simplify because the whole number becomes negative, right? I don't want to do that because I have to write this in which format? In the characteristic and Mantissa format, where I need a positive part for the Mantissa. That's why I separately do this. So 16 into 1.556 gives you 24.896. And the minus 3 into 16 gives you 48. So what I try to do now, I don't add the minus 48 to this number. I'll separate this. I keep it separate. Right? So this is equal to, so when I do the addition, the minus 48 gets added to plus 24, and the answer is a minus 24. But the remaining part remains as it is. So plus 0. This is I think 896. So 0.896. So we have that as our answer. So 0.896. Right, now you can see that this is equal to 24. I can write 24.896. This means I just have to look at the magnitude of the negative part, that is minus 24. So if you want to look at the number of zeros, right? So this implies the number of zeros required is equal to that 24 minus 1. Okay, this is 24 minus 1 because just now we have seen a point, and the point suggests that if you have something like this, then there exists n minus 1 number of zeros. So I'm applying that point now. So n minus 1 is 23. So there are 23 number of zeros. Okay. Now problem to solve. Find the number of zeros between decimal point and the first significant digit of 2 to the power minus 34. Okay. So the answer is, all right. Let's move further. The next topic is the properties of a logarithm. Okay. So let us make an assumption. Let there be two numbers, m comma n, be the two arbitrary positive numbers, right? Let's say a is greater than 0, a not equal to 1, b also greater than 0, and b is also not equal to 1. And let's also assume some numbers, alpha comma beta, right? Both be real. Okay, now we use all these parameters to define the property. So the property number 1 can be considered as, if I have to calculate log of m into n to the base a. This is nothing but log of a product. So this has to be log of m to the base a plus log of n to the base a. Already we know this, right? Log of a product is the sum of the individual logs. All right. Then let's go to the next problem. That is, if at all I want to calculate log to the base a of m divided by n, right? It's a ratio, right? I can try to write that as log of m to the base a minus whatever is the denominator is negative, minus log of n to the base a. And the next property is log to the base a of m raised to the power alpha can be simply written as alpha times log of m to the base a, right? Then let us try to write the next one. if at all I want to calculate log n to the base a, right? This is minus beta. Okay, let me write it as 1 by n to the beta. Let me write in this way. Just a second. I want to write log, this is 1 by n to the power of, okay, let's try to write in this pattern. So this is, if at all I try to write log of n to the power 1 by beta, then I can write it as 1 by beta log a of n. Okay, so this is the representation. Now we have some other notes. So these are the fundamental properties. Now we extend this further. So if we have something like log of a to the base b into log of b to the base a is always equal to 1, right? This also is going to imply you that log a to the base b should be equal to 1 divided by log of b to the base a, right? Obvious. Next, we have another property. If I try to write log of a to the base b into log of b to the base c into log of c to the base a, if at all we try to write an equation like this, that's also going to be equal to 1. Okay, then another property, if I try to write log of x to the base y into, okay, I will change x now because x and the multiply sign looks very similar. So let's write it in this way. If I try to write log x to the base y into the log y to the base z into, I will see log of z to the base a. I change this. This is nothing but equal to whichever is unmatched. Unmatched is x to the base y, y has been cancelled, z also has been cancelled, but a is not cancelled. So log of x to the base a. Right? And one more. The e to the power ln of a to the x. So e and ln are inverse of each other. E to the power and log is actually going to cancel each other. So you have only a to the x as the answer. All right. Then some other properties to add. If I have a to the power log to the base b of x is equal to x to the base log a to the base b. All right, this is possible if b is not equal to 1 and a comma b comma x all are positive. All right, and the next one, this is what we already know, but let's write once again. So this is a to the power log x to the base a is equal to x itself, right? The condition is a should be greater than 0, a is not equal to 1, x is greater than 0, right? So that's the condition. Let me write once. A is greater than 0, a not equal to 1, and x should be greater than 0. If that condition is satisfied, this is fine. Okay, and then okay, if I have a term like log to the base a, this is alpha root of x to the power beta. This is nothing but beta by alpha log of x to the base a, right? Then all right, right? Let's try to solve some problems based on these concepts. First one. Okay, if 3 times x to the power log of 2 to the base 5 plus 2 to the power log x to the base 5 equal to 64, find x. All right, now just have to use the properties, that's all, right? So let's start with the given equation, right? So it says that 3 times x to the power log 2 to the base 5 plus 2 times log x, oh, not 2 into, it is 2 to the power. So this means it is 2 to the power log 5 x equal to 64. So we have one property which says that a to the power log of x to the base b can actually be replaced by x to the power log a to the base b. Okay, so this is the property. So which means I can definitely write like this. This implies 3 times it is 2 to the power log x to the base 5 plus 2 to the power log of x to the base 5 equal to 64. Right? Just we need to identify the properties at the right time. So this was a property which I'm going to use. Right. So this is 3 times something plus 1 time. So this simply becomes 4 times. 4 times 2 to the power log x to the base 5 equal to 64. Okay, 4 into this is 16. So 16 can be written as 2 to the power 4. So comparing the powers, log of x to the base 5 is equal to, it's a 4. Right? So use the basic property of logarithm. So x has to be equal to 5 to the power 4. So 5 to the power 4, 5 into 5, 25 into 25, 625 is, yeah, it is the answer. All right. Okay, very simple. Next. Next question. If 4 to the power log to the base 16 of 4 plus 9 to the power log 9 to the base 3 is equal to 10 to the power log to the base x of 83. Find the value of x is a question. There are two more properties which are actually important. I think I didn't write. Let me write that property first. Right. So there is one note once again coming before the answer. So this is, if you see a to the power log of a to the base b, and it is b is not 10, not any something like not like a previous case, right? Where you see that, right, a to the power log of x to the base b. It's not like that. It's a different one. This is going to be directly root a under some condition. The condition is that if b is equal to a square, right? And there is another one that is a to the power log of a to the base b is actually equal to a square, provided b is equal to root of a. Depending on this, now you see this is actually applicable. I can see that the 4 and 16 and the 3 and 9 are related in this fashion, right? So I can actually rewrite this directly. So this implies, so look at the first this thing, 4 to the power log of base 16 log to the base 16 of 4. So I can see that b is equal to a square. This condition is satisfied here, right? So I can simply replace this as root of a. A is how much? A is 4, right? So I can simply write that as root 4 plus 9 to the power log of 9 to the base 3, right? You can see that there is a relationship. B is root of 9. That is b is root of a. Okay, so when this happens, it is something like a square. So what is a square? A is 9, right? 9 square is equal to, right hand side still remains same, 10 to the power log to the base x of 83. So 9 square is 81, root 4 is 2, so this is 83. 83 is equal to 10 to the power log to the base x of 83. So let's do one thing, take a log on both sides. So that means log 83 means this is base 10, right, equal to 10. When I take the log of 10 to the power, that will cancel out, right? So it's simply log of x to the base 83. Comparing both sides, I can say that x is equal to 10. Okay, this is the required answer.